Hello everyone, welcome to Algebra 1 with Miss Betsy. I'm glad that you're with us today. You're going to have a little bit of a breather with today's lecture because what we're going to be talking about is how we add and subtract radicals. And we're going to see that even though they have to be simplified before you combine them, that this is a pretty straightforward process and you'll get a breather from some of the more challenging topics that we've had lately. Got a story that I want to read to you. It's not a story, it's a joke. It's not even a story I'm reading to you, it's still very early in the morning. What do you get if you cross an alligator with a flower? Well, you know what? I don't know what you get, but I am sure not going to smell that thing. So today we are in section 10.5 in our text, which is Algebra 1 for Christian Schools, published by Bob Jones University Press. I'm using the second edition. We are on page 416. Now, we know that when you combine variables, you can only combine like terms. And a like term that's a variable, the letter has to be the same and the exponent has to be the same. Well, what are like radicals? Like radicals have the same radicand and the same index. Two parts to them, same radicand and same index. And already you are thinking, okay, I didn't get my vocabulary memorized still. What in the world is radicand and what in the world is the index? Remember that the radicand is what is underneath the radical symbol. The index indicates which root you're taking. So this is why you have to simplify radicals before you can add or subtract them, because the index has to be same and the number that is underneath that radical sign, or the radicand, has to be the same. And once you have like radicals, you add or subtract the rational part of that expression. For example, if you had 4 times the cube root of 3, 4 times the square root of 3, plus 2 times the square root of 3. 4 times the square root of 3 plus 2 times the square root of 3. Now, not that long ago, that would have looked like a little bit of a mess to you, but you can recognize this. This is pretty much just like saying we're going to add 4x plus 2x, because we could say let x equal the square root of 3. And instead of using the square root of 3 here, if we substituted in an x, then that just obviously and immediately jumps out at you as, oh, well, that's just going to be, add the coefficients together and we have 6x. If x is actually equal to the square root of 3, when we combine these two radicals, 4 times the square root of 3 and 2 times the square root of 3, it just becomes 6 times the square root of 3. And we talked about this in class the other day, and there's a huge sigh of relief from the kids, and then they said, that's all you do? I said, yeah, it's all you have to do. You have to make sure that you are, just like you can only add x's together, you can't add x and y, you have to have the radical part of your expression being identical, and then you can add it. I said, okay, so this is really easy. I said, yes, it is. However, there's a little bit of a kicker that we're going to worry about. And it's not hard, provided you have learned how to simplify radicals. So let me go ahead and just do this second very easy example. Square root of 5, 9 to the square root of 5, and 2. Square root of 5 plus 9 times the square root of 5 plus, that's a very bad drawing right there. Let me redo that. plus the square root of 2. Square root of 5 plus 9 times the square root of 5 plus the square root of 2. So we have two different radicals here. Square root of 5 and square root of 2. So only two of these are like. You have the square root of 5 plus 9 times the square root of 5. Don't fall into the trap of saying that this answer is just 9 times the square root of 5 plus the square root of 2. Do not do that. Because remember, just like if you have x plus 2x, you combine those, get 3x, because we understand that when we have no number in front of the variable, we're just saying that there's 1x. 1x plus 2x is 3x. Here we have 1 times the square root of 5 plus 9 times the square root of 5. So of course the solution to this would be 10 times the square root of 5 plus the square root of 2. So don't forget that if there's no rational part of that radical expression, that we just have 1, and you have to add or subtract that 1 times whatever the root is. And of course it doesn't end up being like 10 times the square root of 7 where you add the radicands, or 10 times the square root of 10 where you multiply the radicands. This is the solution, okay? So let's go ahead and do a problem where we have to actually simplify the radical. Square root of 12 minus the square root of 3. Now you look at this problem and you remember, okay, Miss Betsy, you said that the radicand has to be the same and the index has to be the same. Index is the same, it's a 2. We understand that we're talking about the square root here, but the radicand is different. So my problem's completed at this point. And you say, well, no, it really isn't, because square root of 3 is simplified. There are no perfect squares in here. Square root of 12 is not simplified. And you'll remember back a period of time ago that when we factor 12, of course 12 can be 1 times 12, 2 times 6, 3 times 4. We're looking for factorizations of 12 that include a perfect square, because we're taking a square root here. 12 is not a perfect square. 6 is not a perfect square. 4, however, is a perfect square. So we're going to be rewriting 12 as square root of 4 times 3. Minus the square root of 3. Remember that you can take this right here, product rule right here, the square root of a product is the same as taking the product of the square roots. The square root of 4 is 2 times the square root of 3 minus 1 times the square root of 3. And what's our solution? The solution then is going to be the square root of 3. This is what I mean when we say that we have to simplify our radicals. Because when they're simplified, you're frequently going to find out that you do have like radicals that need to be combined. Is this clear to everyone? I want to go ahead and point out a different way slightly different way to show this work. I'm accustomed to seeing numbers just written out as perfect squares, but remember we talked about using the exponential form of factors. Here we have, instead of writing this 4 times 3, we can write this, we can factor 12 so that we have 2 squared times 3. When we use the exponential notation here, that allows us to use the trick. Go back, in my class I'm speaking to you, go back to your book, I believe it's section 10.2, where if the index and the radical, the index and the power on the radical are the same, means that you simply have one factor of 2 is a perfect, one of those factors of 2 is a perfect root, so it comes out to the outside, which is spoken very poorly because I truly don't care for that method of using simplification of radical symbols. But if what I did here makes sense to you, or if you want to learn more about this method, let me go ahead and flip back in my book and see exactly where they are using that. Okay, this is what they call the general method of simplifying radicals. It's on page 400 of that Algebra 1 for Christian Schools by Bob Jones University Press. It says factor the radicand into primes, divide the exponent on each prime factor, divide the exponent on each prime factor by the index. 2 divided by 2 is 1. The quotient becomes the exponent on the prime factor outside the radical sign. 2 divided by 2, this power here divided by the index is 2. 2 divided by 2 becomes the exponent on the factor outside the radical sign. So we have a factor outside the radical sign with an exponent of 1. And the remainder becomes the exponent on the prime factor inside the radical sign. 2 divided by 2 is 1, remainder 0. So there's actually a factor that we're not seeing here, 2 to the 0 times 3. Well, you know that anytime you have any quantity raised to the 0 power, that's just 1. So 2 to the 0 is 1. We have 1 times 3. So this is that methodology that we saw in chapter 2, where in section 2 of chapter 10, where if you use the exponential notation to indicate your factorization, you're going to divide the power by the index. 2 divided by 2 is 1. That quotient is the power on the factor outside the radical symbol. The remainder is the exponent on the factor underneath the radical symbol. And if I just spoke total Greek to you, don't worry about it at all. You do not have to use that methodology, but that's something that they revert to frequently in your text. So, slight rabbit trail reminder notwithstanding, we're going to go ahead and continue on with section 10.5 just as soon as I can locate it, come up with our next problem. Now we want to do 2 times the square root of 50 minus 5 times the square root of 8. Two times the square root of 50 minus 5 times the square root of 8. Just like you always have to simplify or reduce fractions to lowest terms, you always have to simplify radicals, and radicals are simplified when there are no perfect powers underneath the radical symbol. Here we've got perfect roots, There are no perfect square roots in 50, no perfect square roots in 8. Is that true? No, it's not true. That's why you have to factor. 50 can be written as the square root of 25 times 2. 8 can be written as 4 times 2. Are there other ways that you can factor 50? Yes, of course. You can say 1 times 50 2 times 25, or 5 times 10. What is the purpose that we are trying to accomplish when we show 50 as a product of two different factors? What are we trying to do? We're looking for a factorization of the number which includes a perfect square, because we're taking the square root. You can't take the square root of 50, can't take the square root of 10, can't take the square root of 5, but you can find the square root of 25, and that square root is 5. Same thing over here when we're taking the when we're looking for the square root of 8. 2 times the square root of 25 times the square root of 2 minus 5 times the square root of 2, square root of 4 times the square root of 2. Now what are we going to have? We have 2 times 5 times the square root of 2 minus 5 times 2 times the square root of 2. Now that right there doesn't look right to me. Let me see what I've done wrong this morning. Nothing. Good thing. 2 times 5 is 10 times the square root of 2 minus 5 times 2 is 10 times the square root of 2. 10 times the square root of 2 minus 10 times the square root of 2 is equal to 0. Notice what we've got going on here. Something that is just so very different. Usually when we're dealing just with numbers, things will jump out to us, and it becomes obvious pretty early on that we're subtracting the same quantities. We're going to end up with 0. But here you see that when you're using radical numbers, doing computation with numbers that include irrationals, you may not recognize at all that you're dealing with the same quantities, because working down through here, I knew that they were going to be the same, end up both being the same values here, but it just didn't make sense to me, which is why I checked to make sure my math was correct. What you do when you're adding or subtracting radicals is make sure that you have each individual radical there reduced to lowest terms, or simplified, if you will. So let me do one last one for you, just so that you can see very, very clearly what we're working with. And then you can just pretty much enjoy working on section 10.5. This is example number 5, and it says simplify -8 times the square root of 5 plus 9 times the square root of 20 minus 6 times the square root of 5. So what do we have to do here? Square root of 5 is simplified. There's nothing you can do. 5 is a prime number. Square root of 20 is not simplified. How are we going to factor that so we have perfect squares? Well, of course it's going to be 4 times 5. So we have -8 times the square root of 5 plus 9. I'm going to skip this one little written step here and say times the square root of 4 times the square root of 5 minus 6 times the square root of 5. And of course our product rule allows me to break the square root of 20 into the product of two square roots. -8 times the square root of 5 plus 9 times 2 times the square root of 5 minus 6 times the square root of 5. And I'm sure that you caught that I had written the square root of 6 instead of the square root of 5, but I caught it as well as I kept going. Negative 8 times the square root of 5 plus 9 times 2 is 18 times the square root of 5 minus 6 times the square root of 5. We can combine all of these into one solution because we have 3 like radicals. They're all the square root of 5. Negative 8 plus 18 is a positive 10. Minus 6 is 4 times the square root of 5. I think you should find these enjoyable. If you're writing all of your steps, it's going to take you a little bit of time to complete those, but I want you writing all of your steps so that you're learning the methodology so that you can go back when somebody says, hey, how did you get from here to here? And you can say, oh, I did it right here. Oh, and right here's the mistake I made. I wrote minus 6 times the square root of 6. Or, when I look at your work, you need to be able to have that work there so that I can go back and say, okay, Susie Q, here's where you had your difficulty. Make sure you're showing me your work. Enjoy this section, and I'll see you next time.